Hello geometry students, my name is Jami Emigh, and this video is our discussion on section 3.2, proving lines are parallel. Let's start with the parallel postulate. We are going to, as you guys know, use this notation right here. I call it the geometric code to denote when we have two parallel lines. I want to point out a little more on the code here. This is a point P on the line. This, however, this lowercase l is not a point on the line. It's just a label or a name for the line. All right, so now that we know what all of that notation means, through a point not on a line, there is one and only one line parallel to that given line. There is exactly one line through point P parallel to lowercase l, to line L, okay? Point P, like that. All right, and that is the parallel postulate. So there's exactly one line through P parallel to L. Let me backtrack a little. The parallel postulate starts with line L, like this here. And now let's walk through it. Through a point not on a line. So I can put this point anywhere. In this figure, you can see they put point P right there. I will go ahead and put it here. And I'll call that point P also, just so you can see that I'm talking about the same parallel postulate. There is one and only one parallel to that given line. So through this, there's only one line that exists that will be parallel to line L and will also pass through point P. And it would have to be this one here. And that is the parallel postulate. Now the perpendicular postulate. Through a point, not on a line, there is one and only one line perpendicular to the given line. So same thing, let's break down the geometric code first. This symbol right here means 90 degrees. It means that it's a right angle, and it means that those two lines intersect are perpendicular because they intersect at a 90-degree angle. Okay, so that code, it means quite a bit right there. You want to pay attention to that. Capital P right here is a point on the red line. Lowercase l is the name of the black line, not a point. And let me erase that work, and I'll just backtrack just like I did last time. It says we're starting with line L through a point not on a line. So I can put point P right here if I want to. And the perpendicular postulate says that there is one and only one line that will be perpendicular to L and pass through point P. And so in this case, it would be this line right here. And we would mark that off with this geometric code right there, the 90-degree angle, right angle, or indication of perpendicular lines. Two lines perpendicular to a third line. Okay, what would be the deal with that? The theorem says that in a plane, so all on one piece of paper, you're drawing this, if two lines are perpendicular to the same line, then they are parallel to each other. All right, it's kind of tricky to wrap your mind around it when you read it in that form, but let's look at it in this notation here and then the figure. So it says that if line M is perpendicular to line T, this symbol right here means perpendicular. And line N is also perpendicular to that same line T. They're using T as transversal as well, just to help you out there. If both of those things are true, then line M is parallel to line N. Now let's look at it on the figure. All right, first condition is that M has to be perpendicular to T. Check, that's right there. Second condition, or also, we need N to be perpendicular to T. Right here, check, got that. Then we can say that M is parallel to N, and that is what allows us to put these arrows right here. Alternate interior angles theorem. All right, the theorem is, if two lines and a transversal form alternate interior angles that are congruent, then the two lines are parallel. Okay, so we've already talked about the definition of alternate interior angles, and I just want to redraw. Like in the definition, the two lines didn't have to be parallel. Let's say they were like this here. Then the line that cuts through them we call the transversal. Okay, so it's kind of obvious that if this is the L we were talking about and this is the M we were talking about, they don't have to be parallel lines for this to be considered a transversal. You can see here these don't look like 90-degree angles. However, this theorem says that if you find two alternate interior angles and those angles are congruent, okay, so let's go to this figure. Angle 4 and angle 6 are alternate interior angles. If those two angles have the same measure, have equal measure, so if they are congruent, then the two lines L and M are parallel lines. And that would allow us to add an arrow here and an arrow here. I'm going to erase that scratch work and try to say it a little differently. If you see two lines cut by a transversal like you do here, and you see the geometric code, this arch and that arch, you are allowed to add the geometric code, this arrow and this arrow. Reason, alternate interior angles theorem. All right, I hope that helps. It could have been the other two. Let's say this was 5 and 7. If those two alternate interior angles, if we found that they have equal measure or are congruent, then again, we could add those arrows saying that the two lines are parallel. All right, I want to just draw this one more time. I know it's not easy to wrap your mind around at first, so I just want you to visualize this where they're clearly not parallel lines. Then the alternate interior angles 4 and 6, look how different they look. 4 is an acute angle. 6, at least in my sketches, looks like maybe a 90-degree angle. So nonetheless, if 4 and 6 do not have the same measure, then these two lines won't be parallel. But if you tweak these lines, if you start to like shift this line right here and shift it so that it ends up parallel to the other one, then angle 6 ends up, let me see if I can erase the old line. There we go. Then angle 6 ends up right here. And now look at the measures of 4 and 6. Once those two lines line up, and by line up I mean become parallel, 4 and 6 will have the same measure. So that's the alternate interior angles theorem. It's one way to prove that two lines are congruent. Okay, identifying parallel lines. Which lines are parallel if angle 1 is congruent to angle 7? Justify your answer. All right, so we have 4 lines here in this figure. And I'm just guessing from the figure, it's either going to be L, line L is parallel to line M, or it's going to be line A is parallel to line B. I mean, those seem like the obvious ones, right? L parallel to M, or A parallel to B. So it's one of those two pairs. And let me erase that scratch work now. All we know though is that angle 1 is congruent to angle 7. Okay, so I want to focus on those. So angle 1 right here is congruent to angle 7. All right, what I like to do at this point is take my 4 lines and I cross out the line that is not included in 4 or 7. So which line, I cross out the line that is not included in angle 1 or angle 7. So which line, A, B, L, or M, has nothing to do with angles 1 and 7? If you said L, you're correct. So you can cross it out if you have these printed or writing on it, or just visually ignore it if you're able to do that. All right, so it turns out that we are talking about two parallel lines, A and B, and M is our transversal. Okay, so if A and B are parallel lines, let's go the other route. If angle 1 and angle 7 are congruent angles, and they are also alternate interior angles, hopefully you can see that, then by our theorem right here, alternate interior angles theorem, we can conclude that A and B are parallel lines. All right, so the trick now is how to justify our answer. We would say that angle 1 and angle 7 are alternate interior angles. If angle 1 is congruent to angle 7, which was the if statement from right there, then line A is parallel to line B, and our justification is by the alternate interior angles theorem. Corresponding angles theorem. If two lines and a transversal form corresponding angles that are congruent, then the lines are parallel. You guys, this is exactly like the alternate interior angles theorem. Alternate interior angles said if you can get two alternate interior angles to be congruent, then you have parallel lines. Watch, it's the same. If you can get two corresponding angles to be congruent, then you have parallel lines. I'm going to even show this one. If you can get, no, that one's supplementary. I'll wait on that one. So corresponding angles 2 and 6. This is the transversal. And if you can get L and M to line up just so that they're, and by line up I mean so that they're parallel, then 2 and 6, you can see they become congruent. So if we know that these corresponding angles right here, 2 and 6, are congruent, then we are allowed to conclude that angle L is congruent, line L is congruent to line M by the corresponding angles theorem. And it could be any pair of corresponding angles. It could have been 1 and let's say this is 5. If those are congruent, those two lines are parallel. All right, so that's our second way to prove two lines parallel. Now we're going to do a third theorem that will allow us to prove two lines are parallel. It's very similar, but there is one little difference. This time, if you can find two same side interior angles and you can say that they are supplementary, then you can conclude parallel lines. Let's look at the figure here. So we have two lines, L and M, cut by a transversal. Same side interior angles, let's look at 3 and 6. 3 and 6, and you can see what from where they're at, that they're, if you're trying to have L and M be parallel lines, 3 and 6 aren't going to be the same measure. 3 is going to be obtuse, 6 in this figure is going to be acute, at least in this figure. I mean, if we shifted the transversal, if we like tilted it over here so the transversal was like this, then 3 would be acute and 6 would be obtuse. But just rambling about that, sorry. All right, so if 3 and 6, if their two measures add up to 180 degrees, if you can find same side interior angles that are supplementary, that means they add to 180, then you can conclude that the two lines are parallel. So if you're able to show this right here, then you're able to add these arrows. There's no real geometric code for those two angles being supplementary. So you just have to show it through an equation that they equal 180, and that'll allow you to conclude that the two lines are parallel. So same side interior angles theorem. All right, so we have 3 theorems now that allow us to prove two lines are parallel. Okay, here's our fourth one, alternate interior angles. If you can find two alternate interior angles and you can show that they are congruent, then you can conclude that the two lines are parallel. Okay, so looking at this figure, same scenario, lines L and M, if they line up, and by line up, I mean if they are in parallel position or parallel lines, then you can see that angle 1 and angle 7, they're congruent. So if you can get angle 1 and angle 7 to have the same measure, so if angle 1 and angle 7 or any pair of alternate interior angles are congruent, then you can conclude that line L and line M are parallel lines. Let me say that a little differently. If you have two lines, L and M, cut by a transversal T, and you see this geometric code, 1 and 7, you're allowed to add this geometric code. Justification, alternate interior angles theorem. All right, let's practice writing a flow proof of the alternate interior angles theorem. So this is the theorem we just covered. We're just going to write a flow proof to see the proof of it. Okay, so we are given angle 1 and angle 7 being congruent. We have that in the given congruency statement right there, but we also have it in the geometric code right there, okay? If they didn't put the geometric code on there for you, I highly suggest you put it on there. Whenever they give you information like this about a figure, you want to put that information on the figure using the appropriate geometric code. So maybe it's congruent angles marking, maybe it's a congruent segment marking, maybe it's parallel lines marking. You want to add that on the figure so all of your information, you have a visual on it like this. All right, given that information, we are being asked to prove that line L is parallel to line M. Okay, we numbered some other angles so that we can reference them. We've numbered 3, 5, and 6 as well. 3, 5, and 6, they have relationships between 1 and 7. Like, just talking this out here. Angle 1 and angle 3, those are vertical angles. See this? Anytime, just try to focus on those two lines crossing, 1 and 3. And we know that vertical lines create vertical angles, and vertical angles are congruent. So that's an interesting thing to recognize. 5 and 7, similarly, those are vertical vertical angles. If you just focus on these two lines here, 7 is here, 5 is here. That's vertical angles. 6 is here. What's the deal with 5 and 6? That's a linear pair. They add up to 180. Same with 6 and 7. 6 and 7 are a linear pair. They add up to 180 also. So they're supplementary. So we have some congruency and some supplementary parts in this figure right here. So let's put all that together and try to prove that line L is parallel to line M. We often start with our given information, angle 1 being congruent to angle 7. Justification, it was given to us. All right, and we're going to state any other definitions, postulates that we know. And so here is a vertical angles are congruent statement. And to state that in a congruency statement, you have to write it like this, and then this would be the justification. So this is the statement, this is the justification. This one here is the statement, this one here is the justification. All right, so now we have two statements. We have angle 1 congruent to angle 7 and angle 3 congruent to angle 1. So I'm going to add a congruency mark on our figure right there on angle 3. Okay, if angle 1 is congruent to 7 and angle 3 is congruent to angle 1, do you guys remember that law of syllogism that says you can cut out the middleman? So 7 is congruent to 1, 3 is also congruent to 1. So angle 3 and 7 would then have to be congruent to each other, which we can see by the law of syllogism using these two statements, but also we can see by that figure. As soon as I added that single arch mark on that angle 3, any angle in that figure with a single arch mark will have the same measure as 1 and 7. So we can state it. Angle 3 is congruent to angle 7. Substitution, or the transitive property. Using reasoning, it's the law of syllogism. So this right here is our statement, and this right here is our justification. Okay, angle 3 is congruent to angle 7. All right, if angle 3 and angle 7 are congruent, look at angle 3 and 7. How are they related? What is the relationship between angle 3 and angle 7. Look at those in the picture. What type of angle pairs are those? If you said corresponding, you're right. Angle 3 and angle 7 are corresponding angles. So, since we have corresponding angles being congruent, we can say that the two lines are parallel. Let me go back. I'll show you that theorem. It's right here. Whoa, that's scratch work on there. It's the corresponding angles theorem. If you can ever get two corresponding angles to be congruent, then you can conclude that the lines are parallel. So this is what we're using in the very last step of our flow proof. Corresponding angles are congruent, then the lines are parallel. That's our justification for this statement right here. And this statement right here is exactly what we were being asked to prove. So notice the flow. We start with what we were given. We state any other definitions, postulates that we know. We use manipulation of substitution, transitive property if we need to, and then we end with whatever it is we're being asked to prove. So this is your start, and this is where you finish. It's kind of nice because sometimes in math you'll ask yourself, like, am I done with the problem? And you'll know if you're able to state what they were asking you to prove with justification, you'll know that you're done. All right. Using algebra to prove lines are parallel. What is the value of x that makes line A parallel to line B? All right, so they're asking us to solve for x, or more specifically, find what x would have to be to make lines A and B parallel. Well, look at those two angles. We need to write an equation, so we need some kind of balance. We need an equal sign, because that's what makes an equation. We need it to have an x in it so we can solve for x. So looking at our information here, do you think we should add those two up to equal 90 degrees? Maybe we should set those two things equal to each other. Maybe we should add those two things up to equal 180. Well, let's explore. Those two angles are, how are they related? Let's see, they're both interior, so they're both on the inside, and they're on the same side of the transversal. So those are same side interior angles. Okay, same side interior angles. For those two lines to be parallel, those were either, same side interior angles either had to be congruent or supplementary. Do you guys remember which one? If you said same side interior angles need to be, where is that postulate? There it is. If you said same side interior angles need to be supplementary to have the two lines parallel, then you got it right. Okay, so we're going to set those two angles, their sum, equal to 180. All right, and that is how we will translate from a geometric figure into an algebraic equation. So we have this angle right here plus this angle right here needs to add up to 180 degrees to make A and B parallel. For that to happen, x would have to be, we combine the 9 and the 111 right there, subtracted 120 from both sides of the equal sign, that's the subtraction property of equality, and finally divide both sides of the equal sign by 2, that is the division property of equality. And so it turns out that x would have to equal 30 for those two lines to be parallel. Notice it doesn't say x equals 30 degrees because x is not the angle measure. It's just the variable in the algebraic expression for the angle measure. So keep an eye out for that too. If x is in the expression, you don't write x many degrees. Let me just take a second to check our work. Not only is it quick and helps you not to lose points for small things, but it also can help you to understand what in the world you just came up with. So let's say x is 30. So I'm going to plug it in right here. So that would be 2 times 30 plus 9. That is 69-degree angle. Write that right there. And this one is 111 degrees. Do those add up to 180? That'd be 170. Yes, they do. They add up to 180 degrees. And because those same side interior angles add to 180 degrees, we know the lines are parallel by the same side interior angles theorem. All right, I know that was a lot. Ultimately, those were, I think we had 5 different ways of proving that lines are parallel. So if you're ever asked to prove 2 lines parallel, you might want to go back to this video and see those theorems that will justify you doing so. Okay, thank you for joining me. That will conclude our discussion on section 3.2. My name is Jami Emigh, and I will see you next time for our discussion on section 3.3.